Hello and welcome to the course From Data to Decisions. I'm Chris Mack, your professor for this class, and this is Lecture 21, where we're going to introduce a topic that might be new to most of you, a topic in regression called leverage. Now, in the last few lectures, we talked about outliers. We saw that since we frequently use non-robust estimators for mean, standard deviation, and regression, like ordinary least squares regression, that an outlier can have a huge influence on regression results. It can pull the whole regression model way away from the rest of the data because of that influence of that one outlier. Well, outliers are data points that have extreme values in y, predictor variable. But there's another concept called leverage. Data points with leverage are points that have extreme values in a predictor variable, x. And as a result, high leverage points can influence regression results in a similar way that outliers can influence regression results. Now, in the next lecture, we're going to define what we mean by influence much more carefully. Now it's just kind of a vague concept. But I can define exactly what I mean by leverage now. We look at the distance that the x values have, one to the other, and accounting for the correlation, explain which x values have more influence or leverage on the regression results than the others. That might seem a little vague, but some examples might help in just a few slides. Mathematically, we're going to define the leverage as the diagonal elements of the hat matrix. Now, you go all the way back to lecture 6. We talked about ordinary least squares regression using matrix math. We defined something called the hat matrix, H. We said that the hat matrix puts a hat on Y. So Y is our experimental response variable results, our measured outputs of the experiment, and put those in matrix form, multiply by H, and we get the predicted values of our model. H is calculated from the x variables in this way. We don't need to remember that other than to know that a piece of software is going to do that work and calculate the hat matrix for us whenever we do ordinary least squares regression using matrix math. Now, the diagonal elements are going to be what we call the leverage. And specifically, they are the covariance of the modeled result and the experimental result for each data point, normalized by divided by the variance of each data point. Now, that normalization means that diagonal elements of the hat matrix must always be between 0 and 1. Also, I'm not going to try to prove it to you, but you could prove this simple theorem that the sum of all of the diagonal elements of the hat matrix, the sum of all the leverages, must equal P, the number of parameters in the model. What that means is, on average, the leverage is P over N. So if we've got a model with a certain number of parameters P, say there's 2 parameters, and N is the number of data points that we're using in our regression, let's say it's 20, then we divide those two, and that says, on average, a typical value, an average value of the hat matrix is 0.1. So what we'll do is we'll compare the values of the leverage for each data point to this average value, and in that way decide whether we think it's big or not. As I said, for ordinary least squares regression, we generally will use matrix math to do the calculations for us. But for the case of a single predictor variable, we also know that we can perform the calculations by hand fairly simply, and we've done that earlier in the course, the first few lectures. We can also calculate the diagonal elements of the hat matrix analytically with a simple formula for the case of only one predictor variable. And here it is. All right, so this is what it turns out to be, and very, very simple formula. We calculate the mean of all the x values, standard deviation of all the x values. Remember, these are for the experiment. And then we calculate the leverage of each data point using this formula. When we get to multiple regression, we have more than one input variable for our model, then we don't have a simple formula to use, and instead we'll just use the matrix math to generate those values for us. Let me try to explain the meaning of leverage through one of the examples that we saw in Lecture 8. Remember, Francis Anscombe had this fabulous paper where he talked about things that can go wrong with regression, and high leverage was one of them. So here's a set of 11 data points. 10 of them have the exact same x value and a spread in y. But one of them has a very different x value. And when I fit the least squares regression line, even though there's 11 data points, really it's only 2. Right? I've got the average of these 10, which turns out to be right there. And that sets 1 point in the line. And then this 11th data point sets the second point in the line. That second data point, the 11th one out here, has a leverage of 1. Whereas the 10 data points that determine the other endpoint of the line, they share responsibility for figuring out where that other endpoint of the line is, and they have a leverage of 0.1 each. So very different leverage. And I think you can get an intuitive feel for what that means. If I move this data point up and down, the least squares line follows it exactly. It has 100% leverage. Wherever that point moves, the line moves with it. But if I were to take one of these data points and move it around, it only influences this end of the line by a factor of 1/10 because of the fact that there's 9 other data points also influencing that point. All right, let's see what leverage means when we start looking at the residuals of our fit. When we began our discussion of regression, we saw that ordinary least squares regression had a number of assumptions, and that we needed to test some of these assumptions. And we began by testing assumptions like, are the residuals normally distributed? Are there any outliers in our residuals? So another thing we're going to ask is what about the leverage? And how does that influence the residual? So our model is for linear regression, looks something like this. Y is some function of the input variables x, and there could be more than one of them. Parameters of the model, beta. And then the difference between the data and the model is the residuals. And we assume the residuals are independent and identically distributed with a normal distribution, zero mean, and a constant variance. That's all well and good. That's what our model is. But when we fit a sample data set to this model, we replace the betas with estimates of the betas. We'll call them B's, BKs. The results of the residuals do not have constant variance. And the reason is leverage. Points with high leverage have lower variance. That makes things a lot more complicated when thinking about how to test our residuals, because they won't have constant variance. So again, when we have the ideal model, if we knew what all the true parameters were, the betas of our model, we could see what the true residuals were, and they have, by assumption, a constant variance. Our unbiased estimator for that variance looks like this. Recall that we divide by n minus p whenever we calculate the variance of our residuals. But we don't know the true parameters, and we don't know the true residuals, and so we estimate them with a fit residual. I'll use epsilon to represent the true value of the residual, e to represent our estimate of that residual based on the estimates of the parameters in the model. So this is the only thing we can actually get at. This is the thing we calculate when we do our best fit, is the residuals E. Well, the variance of each of these residuals is not constant. It's the true variance of the residuals multiplied by 1 minus the leverage. The standard error of each residual then is the square root of that, and we'll estimate the variance of the residuals by our unbiased estimator. The square root of that is the standard deviation to fit residuals. So using that as our estimate, we see that the standard error of each individual residual is the standard deviation of all the residuals multiplied by the square root of 1 minus the leverage. You can see what's going to happen here. When the leverage approaches 1, the standard error of the residual goes to 0. This is the perfect example, this Anscombe problem that we saw before. No matter where I put this far right data point, the fit will land on that point exactly. It will never have a deviation. The residual will always be 0 for that data point, and no matter what sample I get, it will always be true. Zero residual then therefore has 0 variance as well. That's because the leverage is 1. No matter how much uncertainty there is in the y value, the fit's going to hit it perfectly. So we need to understand this concept of leverage if we want to interpret residuals from our data fit. All right, this brings us to how to relate residuals to the work we've done before. We've done some testing of normality and testing for outliers in some of our previous lectures. How do we perform those tests on residuals, which is kind of the point here? Well, since the standard error of every single residual, the standard error of every single residual can be different. When we studentize our residuals, we have to use a different standard error each one. So we will studentize and test only studentized residuals whenever we're doing skewness test or Shapiro-Wilk test or Grubbs test or plotting QQ plots, whatever we're doing. We're going to studentize the residuals first. To do that, we have to know the standard deviation of all the residuals, but we also have to know the leverage residual. This is what we'll call the internally studentized residual. Sometimes it's called the standardized residual, and we'll use this formula to do it. The internally studentized residual, however, is not the only way to studentize our residuals. There's also something called the externally studentized residual. The externally studentized residual excludes the ith data point from the calculation of the standard deviation of the residuals whenever we want the studentized residual of the ith data point. So basically, I'm asking what is the studentized ith residual, but assuming the standard deviation excluded that one point. Well, it turns out that the ESR and the ISR have a fairly simple algebraic relationship with each other, so that once I've calculated the internally studentized residuals, which is, of course, this easy formula to use, I can convert it to externally studentized residual using this formula. Again, I won't try to derive that for you, but it's fairly easy derivation. This externally studentized residual is also called studentized deleted residual. So you'll see these different names being used in the literature. Why two different ways of studentizing? Is one better than the other? Well, it turns out that the sampling distribution of the internally studentized residual is quite complicated. complicated enough that it's a kind of a pain to use. However, externally studentized residual has a very simple sampling distribution. If the true residuals in our model are normally distributed, then the externally studentized residuals will be t-distributed. Kind of what you normally expect, for example, when looking at the residuals of a univariate data set compared to its mean. We can studentize those, and we generally expect that to be t-distributed as well. So that's the nice thing. If we use the externally studentized residuals, well-known and easily understood sampling distribution, we can do tests on it to see if, in fact, the residuals match a t-distribution, which then becomes evidence that our true residuals match a normal distribution. Now note that the degrees of freedom for the sampling distribution will be n minus p minus 1. So n minus p is the number of degrees of freedom when you subtract out all the parameters of the model, and then minus 1 from the calculation of the standard deviation residuals themselves. All right, now that we've defined the externally studentized residuals, we can start doing work. We take a model, we do an ordinary least squares fit, get the best fit model, we subtract the data from that best fit model from the data, that gives us residuals. Then we calculate the externally studentized residuals using the formulas on the previous page. Once we have those, we can start off doing all the kinds of tests that we want to test. If you want to do QQ plots, look and see if the distribution appears approximately normal. Well, you should do those tests only on the externally studentized residuals. If you want to do moment testing, skewness, and tails, are they heavy or not? The moment testing should be done only on the externally studentized residuals. Grubbs test, Dixon Q test, any of the outlier detection or rejection schemes that we've talked about over the last few lectures also must be done on the externally studentized residuals. There's some other tests we're going to be learning about over the next coming weeks as well. Again, always on the externally studentized residuals. And the reason is simple, just like we've said a moment ago. The ESR has a simple sampling distribution, students t, and it allows us to do statistical tests. I'd like to finish this section on leverage by mentioning a graphical way of evaluating your residuals. This is a very simple but powerful graph helping us judge whether we have any problems with our residuals before we do any statistical tests. What we're going to do here is plot the absolute value of the externally studentized residuals versus the normalized leverage for every single data point. So we've got our data, we've calculated all these externally studentized residuals. To do that, we had to know what the leverage was, HII. We know that the mean value of the leverage is going to be P, the number of parameters, divided by N, number of data points in the data set. So if we plot the magnitude of the ESR versus this normalized leverage, we get a set of points that looks something like this. Well, this can tell us a lot because we could plot on the same graph Grubbs critical t-value that we get from doing your basic outlier test. We're not doing it to potentially reject any outliers, but simply to graphically decide whether we have things that are near or further away from this Grubbs critical t-value. And here I see 3 data points, and 2 of them are really close to that critical value. I forget which I think I used 0.01 for the significance level, but I can't remember now when I generated this graph. But we have one that's a little bit further away, so that might be the one that we worry about. But also plotted on the same graph is the leverage. Remember, since I've normalized this leverage, 1 means the average. So this is the average leverage of all the data. So below 1 is less leverage than than average, and above 1 is more leverage than average. So let's plot a vertical line at exactly 2. Now, it's an arbitrary cutoff, and it's not really a cutoff. It's just, again, a graphical tool to help us see what's going on. But it's kind of a standard cutoff that we use, twice the average leverage. Any data points that fall above the Grubbs critical T are potential outliers. Any data points that fall to the right of the leverage equal 2 line is potentially a high leverage data point. And you can probably imagine what we're going to be doing next. If you have data points that are both high leverage and potential outliers, those are data points of concern. Here, our potential outliers have fairly low leverage, so even though they're deviating significantly from what we expected, assuming a normal distribution, they're not having dramatic leverage in our fits. The 2 high leverage data points, notice they have very small residuals. So even though they're high leverage, they're fitting quite well. So to refine what we mean by this, we're going to have to define something called influence, and we'll do that in the next lecture. In the meantime, what have we learned? In Lecture 21, you should be able to quickly and easily answer each of these questions. If not, please go back and review the material. Define leverage. What is the role of the hat matrix in determining leverage? What is the difference between internally and externally studentized residuals? How should residuals be studentized for statistical testing? And finally, know how to create and interpret the Williams graph. Well, as I said, next time we'll extend the concept of leverage to include an even more important concept called influence in regression. Till then.